Okay, so let me start. In the last class, you looked at some of the cryptanalysis. Okay, and you might have observed that it is kind of tedious process in many cases. So question is, or so sometimes you know that we are able to break the crypto system, right? So the question is, how do you make sure that a given crypto system is secure? And Shannon gave that idea, you know, around 40s or something, when he talked about perfect secrecy using ideas from probability theory. As you know that Shannon also gave the fundamental bound when you're transmitting information from one place to other place, right? Or data compression, how much you can compress, right? So similarly, he also talked about uh, perfect secrecy. It's a very nice paper which you can look at it. So in order to understand that perfect secrecy, so I think today I'm going to give you the basic background of I'll just recollect. I think you might be knowing all these things. Some idea about discrete random variables and so on. Then you can look at the plain text space, ciphertext space, and the key space. How you can look at it as a random variables, and then what is the condition for the perfect secrecy, right? Now towards the end, I will show you that one of the crypto system is perfectly secure. So when we say that crypto system is perfectly secure, that means EKS is infeasible, right? That you cannot actually break the crypto system, right? So let me start with the basic stuff. So there are three classifications which are very common. We say that a crypto system is computationally secure. What do you mean by computationally secure? If the best algorithm for breaking it requires at least n operations, capital N operations, and capital N is very large. Okay, so then we say that it is computationally secure. Okay, probable secure if it is based on some difficult problem. For example, if a given integer cannot be factored, so we have built RSA crypto system on that. Okay, so it is probable secure. Then there is an unconditional secure if it cannot be broken even with infinite computational resources. Okay, so essentially with the idea of computer science or the computational things, if a system cannot be broken even if you have infinite computational resources, this is unconditional secure, right? There is no condition, right? Probable secure if it is based on some difficult problem like integer factorization. I think you might be remembering that factorizing an integer is a very difficult problem. For example, even if you want to factor 2000 digit number, Umesh Vajarani has given an estimate that if you assume that every particle in this universe is a classical computer that we use today, right, and it computes up to the age of universe, it will be insufficient to factor a 2000 digit number. Such a difficult problem. So certainly, that's why we are using RSA, because it's so difficult problem, right? So this is the broader classification: computationally secure, probable secure, and unconditional secure. Okay, so now I think you might have done this course on elementary probability theory, right? Discrete random variable is a very common concept. I think many times in some of the in interviews, if you are appearing for a communication company, they do ask these kind of things. Okay, what is random variable? If you don't understand what is random variable, then it's difficult for you to do anything else. Anyway, so what is I'm going to talk about discrete random variable, DRV. So a discrete random variable X consisting of two things: a finite set X, and a probability distribution defined on X. Okay. Okay. So a discrete random variable consisting of a finite set X and a probability distribution defined on X, right? So probability that the random variable X takes on the value X. So probability that a random variable takes the value X. Okay. So we denote it by PR X capital is equal to X. I mean, normally they write it in bold, or in short, we write it as PRX. Okay. Now, obviously, there are some properties that PRX is always non-negative for every x in X, and summation of all the probabilities will 1, right? Okay, so this is a very normal condition. So discrete random variable consisting of a finite set X and a probability distribution associated with it, right? We denote it by PRX. Okay, fine. Now, as an example, if X is, in a coin toss, head or tail, right? So coin toss is a discrete random variable. So probability of occurring head and tail is half, right? So that is the probability distribution, right? Both will come with half probability, right? Also, some observations. Suppose X is a discrete random variable defined on a set set X, and E is a subset of X. Then the probability that X takes on values in the subset E is probability when X belongs to E. We write it like this, okay? So, or sometimes we write it like probability of X when X belongs to E. So we are restricting to that subset, okay? These are the common notations. Okay, now again another example. Random throw of a pair of dice. So if you are throwing 2 dice, right? Pasa they call, right? Huh. So random variable Z defined on the set. So there are 6 possibilities, right? So 6 cross 6, right? I mean, for each dice there are 6 possibilities, right? So Z is this cross this. So probability of IJ is 1 by 36, right? For each one, right? For every IJ in Z. Now we can ask different kind of questions. Consider the sum of the 2 dice, right? Suppose we want to compute the probability that the sum of 2 dice that appears on the face value is fixed, say is 4, right? So then we know that S4 is, what are the pairs? 1, 3, 2, 2, 3, 1. These are the possibilities, right? And so we can compute probability of S4 will be 3 divided by all possibilities, 36, right? Which is 1 by 12, right? So Sj is basically event that the sum is J for the 2 face values, right? So, I mean, you can compute for what the sum value will be 2, 12, 4, 10, all these probabilities. Easily you can compute, right? So you can refresh the. I think we have done this probability course in second semester or fourth. Okay, fine. So you know all these things, right? Good, but we need to recall because people forget. Anyway, joint probability if X and Y are discrete random variable on set X and Y. The joint probability distribution, right? PRXY is the probability that X takes on the value X and Y takes on the value Y. Then we have this conditional probability of X condition Y, right? The probability that X takes on the value X given that Y takes on the value Y. Then independent random variable, if PR of XY is PR of X, PR of Y for every X in X and Y in Y, right? If this happens, it is a independent random variable, right? This is also clear. Okay. So we have basically, that condition. So PRXY same thing as PRX condition Y and PRY, and you can interchange. So this is straightforward. In fact, we have this bias theorem which you might have studied. If PRY is positive, then probability of X condition Y is probability of X times probability of Y condition X divided by probability of Y, right? And obviously, a special case of this theorem is this corollary. If X and Y are independent random variables, then probability of X condition Y is probability of X for every X in X and for every Y in Y. So this is a very popular theorem. I think you know. Again, so as an example, random throw pair of dice defined on the set, 2 to 12. So considering the sum of 2 dices, right? So if Y is a random variable which takes on the value D, if 2 dices are same and value N otherwise, then again we can compute the probability in each case, right? It's very straightforward. So let me we can talk about now perfect secrecy. Now I am going to, so this was just basic elementary probability theory that you know. Now I am going to look at plain text, ciphertext, and the key space and see how they can be looked at as a random variable things. And then from there we can derive the condition for the perfect secrecy. So a crypto system PCKED. P is plain text space, C is ciphertext space, K is key space, E is the encryption rule, and D is the decryption rule, right? And those conditions are there. Uh, okay. So now there is a probability distribution on the plain text P, right? So we can say that plain text elements define a random variable X. Okay, so we denote it by probability of X is equal to X, right? Assume that the key is chosen using some fixed probability distribution. So the key can be chosen using some fixed probability distribution. So key also defined as a random variable K bar, right? So we are writing K, capital K, you can say that. Probability of K is equal to K, right? So some key is chosen with fixed probability distribution, right? Fine. We can also talk about ciphertext. We assume that the key and plain text are independent random variables. Now C, the ciphertext element, we can also think of as a random variable Y. So probability of Y is equal to Y. So X is a plain text, Y is a ciphertext, right? So for a key K in K, we define CK. So encryption of X such that X is a plain text is set of possible ciphertext if K is the key. So CK is the set of all possible ciphertext. Okay. Now I can compute this for every Y in C. Probability of Y is as Y equal to Y is this summation is over for each key, right? Okay, and Y is in CK, the ciphertext. So Y is a ciphertext. So probability of K is, so this K is chosen, the key times probability that X is equal to decrypted with this formula, right? Y is a ciphertext, and this is the decryption rule. Okay, so this is the simple observation that the probability of Y is equal to Y is this sum. Okay, fine. Now observe that for any Y to be the ciphertext and X to be a plain text, probability of Y is equal to Y, condition X is equal to X is summation. Probability of key K is chosen and summation is over for each K such that DK is the decryption rule from ciphertext to plain text. So you can, using Bayes theorem, we can compute this value. Okay. So X is equal to X and Y is equal to Y will be probability of X equal to X times, you know, the overall thing that we've just computed, right? And divided by this probability, you know, with K is equal to K and for the decryption rule, right? So I think we can simplify this value here. This is just Bayes theorem we have applied. So let us take an example actually. If P is plain text A comma B, and since I am saying this is a random variable, so we say that probability of A is 1 by 4, probability of B is 3 by 4. Okay. So probability distribution is there. K is K1, K2, K3, our keys, right? And for each keys, we have the probability distribution. So probability of K1 is 1 by 2, probability of K2 and probability of K3 is 1 by 4. And suppose ciphertext is 1, 2, 3, 4, right? With encryption rule, EK1 of A is 1, EK1 of B is 2, EK2 of B is 3, and EK3 of A is 3, and EK3 of B is 4. So essentially, these rules, these encryption rules, we can summarize in the form of this encryption matrix. So A, B, and the different keys. So you can see that EK1 of A is 1, right? Or if I choose EK3 of A is what? 3. EK3 of A is 3 there, right? Or EK3 of B is 4. So all these rules we can capture in this matrix, right? Now, can I compute? So probability of the plain text is given, probability of the keys are given. I can compute the probability of the ciphertext. How do we do that? probability of 1, if I have to compute probability of 1, so 1 is coming here where ek1 of a is equal to 1, right? So ek1 of a is equal to 1, so that means I need to choose key as k1 and the plain text as a. Plain text probability is 1 by 4, which I have put here, times. Now I have to put the probability of k1. K1 is half. So I have just substituted this half here. So this is equal to 1 by 8, right? For 1, ciphertext 1, the probability we can compute. Now suppose similarly I want to compute for 2. So 2 is coming from here. If you look at the list, 2 is ek2 a is equal to 2 and ek1 b is equal to 2, right? So 3 by 4 is what? For b. So this is for b when we are taking this one. So for b, the probability is 3 by 4 times for k1. K1 is half, right? Plus the other rule is ek2 a is equal to 2. So for a, it is 1 by 4 times k2. K2 is what? 1 by 4. So 1 by 4 into 1 by 4. So overall is 7 by 16. I hope it is correct, right? So like that, we can compute for each ciphertext 1, 2, 3, 4 these values, right? So I think now you understood that if there is a plain text, we have the plain text random variable. Ciphertext, we have ciphertext random variable, and key space we have random variable, right? For each of these things, and how we can compute, right? One or the other. Any question here? It's okay. Okay. And we can also compute the conditional probability. I'm not computing this, leaving it as a T exercise. You can, yeah, you need to drink some cup of tea today, also Saturday, right? So you can compute the conditional probability anyway. Now I am defining what is perfect secrecy. So I think first I covered some elementary probability theory, which you already know from probability 101 course. Then I talked about how plain text, ciphertext, and key space are converted into random variables, right? And then I gave you one example. Now we are ready to define. So if a crypto system has perfect secrecy if the conditional probability of x with respect to x with y is same thing as probability of x for every x in plain text and y as in the ciphertext. This is the condition for the perfect secrecy. So let me show you as an example this theorem. Suppose that the 26 keys in the shift cipher are used with equal probability 1 by 26. Then for any plain text probability distribution, the shift cipher has perfect secrecy. I have to prove this fact. Okay. So I'm going to do only this one example, but I invite you to whatever crypto system you saw. This is about shift cipher. What other ciphers you saw? Affine cipher and all others. So you can actually just take and try to assume some probability distribution for the key and then see whether it is secure, perfectly secure or not. So you need to just check the condition, right? So I think this is not very difficult, but I'll just I'll show you the calculations. How do we show that? That for any plain text probability distribution, the shift cipher has perfect secrecy. But we need to assume this fact that the 26 keys in the shift cipher are used with equal probability 1 by 26, right? That is the assumption. Okay, if we do that assumption, then I guess we can show you this. So PCK is Z26, which is fine. And for any k between 0 to 25, encryption rule is x plus k mod 26. Okay. So we compute the probability distribution on C. So let y is in Z6, the ciphertext, right? Y is the ciphertext. Remember, the probability of y is equal to y is this summation k in Z26. Probability of k is equal to k times probability of x is equal to dky. The previous formula, right? So now this probability we know is 126, right? 1 by 26, our assumption, right? So this will come out. We are left with this. Decryption rule is y minus k, right? So probability of x bar is equal to y minus k. K is in Z26, right? Now probability of y is 126 for any y in Z26, right? So this is whole thing is written as probability of x actually is equal to x. X is Z26, right? And this whole sum is actually 1. You can clearly see that, right? This whole sum is 1. Obviously, the probability sum is 1. So we have here uh, probability of y condition x. So remember, I have to compute this probability of x condition y, right? So first I compute probability y condition x, which is probability of k is equal to y minus x mod 26. Again, we do the calculations. So for every xy, there exists unique key k such that encryption of x is y. So k is equal to y minus x mod 26. So probability condition x, probability of x condition y is equal to this, right? Probability of x times probability of y condition divided by probability of y. Probability of y condition x turns out to be 126 here, and this is also 126. So this whole thing will cancels out, and you are left with probability of x. So that means probability of x condition y is equal to probability of x. So we have perfect secrecy, right? Simple formula, just calculations. We have the perfect secrecy. That's all. So we talked about perfect secrecy. I think if we go I think there should be a characterization left now. So okay, so I think so we need to have some characterization of perfect secrecy. I think in the last, so all these slides are from the last year. As you know that most of the, when I was writing, it takes more time. When you don't write, it takes less time, right? Just show that. So anyway, so I think we will not do this today. What we can actually, so at least you understood what is perfect secrecy. So I invite you for today evening. Just try to see all these things I can ask you in the exam also. All these are T problems, right? So I'm asking you whatever crypto systems you know. I talked about only shift cipher. You check whether they are perfectly secure or not by computing these probabilities, right? The conditions, right? Okay. So this is an exercise for you. That's all, right? Jada burden nahi lena, right? So that's all. At least you have something to play with, and then we can meet in the next class about characterization of perfect secrecy.